research, which took place in the summer after my final year, was in an internship under the supervision of Dr. Shane O'Sullivan, and it was based on discovering new pulsars with LOFAR. And LOFAR is a low frequency array. It's essentially a bunch of smaller omnidirectional radio telescopes scattered across Europe, with the intention of joining them together through interferometry to create one large telescope with a diameter of 1,000 kilometers thereabouts. And the reason you want to do that is to get high resolution, because it's very difficult to get high resolution images of radio astronomy because of the physics behind it. So it's very useful to do this sort of search with LOFAR because you can get higher accuracies for a lot of your measurements compared to conventional radio telescopes. So what are pulsars? A pulsar is kind of tricky to explain at this point because there's new research that came out to found out it might have been something else. But essentially, when a star dies and goes supernova, it leaves behind a core, and these cores, due to like the conservation of momentum and magnetic fields, start to spin faster, such as when a figure skater is spinning with her arms out and then pulls them inwards and spins quicker. That happens from the scale of our sun down to about the size of a city. So they spin a few thousand times a second, and their magnetic fields become about 1 million times stronger than the strongest magnet ever placed on the Earth. And that magnet destroyed itself instantaneously, so quite strong. They're typically thought to be neutron stars, which are core remnants distorted by neutron degeneracy pressure. But it's been found out in 2017 that white dwarfs also experience or exhibit pulsations, and they're supported by electron degeneracy. But these are still very interesting objects because they're compact and they're on the extreme end of what we think matter is, going on to black holes, which is a very blurry line. So it's interesting to find these to understand more about that, because only 3,000 or so new pulsars are known. As I said, they're compact, fast rotators, and their magnetic fields are very strong, but the magnetic field is misaligned with the rotational axis. So you get this lighthouse effect, which will send a beam across a cylinder like that rotates, and that cylinder will pass Earth's line of sight with every rotation. And we'll see like a few thousand pulses every second if they're millisecond pulsars. They can be X-ray if they're magnetars or their experience accretion, but I was focused on radio, which is just the acceleration of electrons off the surface due to the magnetic fields. And this emission is intrinsically polarized. So that's also a very interesting aspect which we were looking for. And they're also made of nuclear pasta. So we don't know what the matter inside of these stuff looks like, but we have a good idea. And it's called nuclear pasta because of how it arranges itself in simulation. It looks like a lasagna, essentially, or other types of pasta. And the first pulsars were discovered in 1967 by Jocelyn Bell, and her supervisor stole the credit, just for all the female scientists out there. And this is a picture of a neutron star next to Manhattan. So you can see how small they can be, and they have the mass of about 1.4 times our sun. So they're quite heavy and dense, and they will kill you if you go near them. So for the intents of my research, we're looking at what pulsars are, and they're highly polarized. So you'll see like 70 to 80% polarization, maybe 100%, down to about 10, which is unlikely seen in other objects. They're compact, so the resolution is as low as we can get it, which is why we'd like to use LOFAR, because you get highly resolved images. The ones we will pick up are mostly within our galaxy, and they typically don't tend to have optical or IOR components when we're looking at them, and that's we won't see them with like normal telescopes normally. So I include mostly. And active galactic nuclei and artifacts from observation will look similar to these, so we have to find ways to get rid of them. So here I've shown an image of an AGN, or an active galactic nucleus, which is a black hole like that at the center of our galaxy that's experiencing accretion. And that was the top one. So we'd see that there's an IOR component next to the black blob, which is the radio. And below it is a pulsar I found, which is visible in radio, but not in the visible. Yeah, that's hard to say. So why we're looking for them is because we can get loads of scientific knowledge out of them. So we find that pulsar physics is still in its infancy, and there's only about 3,000 known. We can probe them for cosmic magnetic fields by using rotation measures, which is essentially seeing how much the polarization rotates on its way to Earth. We can also use them for setting constraints on general relativity, as the first gravitational waves were found to be from two pulsars merging, and we found this based on the amount of energy that they lost before they disappeared. And we could also use them for insights on binary stellar evolution, or just stellar evolution in general. So as I was saying, we don't quite know what the difference between these compact objects and black holes are yet. There's a very blurry line where there's just a jump in mass, and we need to kind of figure that out if we want to understand more about black holes or neutron stars in that matter. And we just don't know enough about them, really. So I went about finding them using an automated, can't think of the word here, pathway to automatically remove sources which were less than 1.5% polarized. So picking out typical AGN and all that, and other radio sources. If they were separated from the image with what, okay, so this is difficult to explain. So there's a separation of where the image is and where we absorb the polarization source. And if that's less than, or if that's greater than 10 arc seconds, which is a very small unit, then we would just kick that out. And you can see on the top one, there's a galaxy here, which is spitting out two clouds either side. And the separation on the top one is about 16 arc seconds. Although it should be much larger, because the center is about where the cross is on that top image. But it wouldn't pick that up. So the bottom one is a pulsar, which is about 8 arc seconds across, but the separation is about 1 arc second, which is very little. So we're trying to isolate those. I also tried to remove all sources that weren't on the LOFAR 2-meter sky survey, which is this image here, and the data release 2, which is including the larger black blobs on the edge. So I tried to remove them so I can get nice clear images using a previewer, because it was much more difficult to extrapolate the images from the actual data, because I didn't have enough time to go through all that. And if they had a low intensity, I would remove them as well. And if the resolution wasn't that great, or they had an optical component, I would remove them. So I did a lot of this using image processing, but I also did it by going through it, the data itself, using an automatic 5-line. And I came up with a few of these. Oh, sorry. And there's also 3,000 known pulsars, and I caught about 100 of them because they're in the same region. And as I said, I removed extended or diffuse surfaces, and I also removed sources if they had a nearby bright star, or if the field was corrupted due to bad data. And I also went to this map here, which is the galactic rotation measure map, and selected the rotation measure for every location that I'd found a new pulsar or pulsar candidate. And I'd added that to my database for later purposes, which I'll explain. And this was the result of my internship. So I'd found about 20 high priority results, but I had also found a lot of low priority results, about 100, but they had corrupted fields or they are nearby bright sources, which might have given them better or higher polarizations, or it just skewed the data to make it look like they were when they weren't. So these ones were all very clean and there's no other explanation. And for a lot of them, there's multiple observations, which is a very good point because then it means that it's less likely to be an artifact because the way the artifacts are formed with the radio astronomy. I don't quite understand it, but it's unlikely to get the same thing twice. It's kind of like when you have cataracts and you see a pattern in your eye, but I don't know how to explain that. So I plotted the galactic rotation measure, which I picked up from the map, and plotted it against the rotation measure we got from the LOFAR observations. And we expected a straight line because we expected all our pulsars to be in a within the galactic plane. But as you can see on this left hand, there's a little dip at about -50, which means it's either really close or really far away, and we just don't know. And then there's also another outlier which I can't explain. And on the left is my on the left is my knowns, the ones that are already known, and on the right are the ones that I'd found. So it's a correlation, but it's not as tight as I'd like to be. But it's still not a flat line, which you would expect with artifacts. As you can see, with I picked out a bunch of artifacts and I plotted them the same way, and it gave very obvious results that these are all fake, except for this one outlier, which I couldn't explain. And my work is being followed up on as we. I believe a lot of maybe about 7 of them are currently going up for observation. I'm not quite sure. I haven't spoke with my supervisor yet. Sorry, and we've updated the known pulsar list with our better positions and rotation measures, which can be used to extrapolate the magnetic fields. And we're just going to continue the search. So that's everything.
Great stuff. Great stuff. I'll just stop the recording.